Hey guys, Math 5500. The first time I taught this class, our program was partially online at that time, and we had on-campus visits. And I remember at one on-campus visit, I was at the board and I was teaching, and thought I was teaching my tail end off, and we were doing some advanced stuff. And one of the students raised his hand and said, "Dr. Darbro, what's a p-value?" And I guess I taught the class with the assumption that students understood those understood a p-value, to be precise, but I found out that they didn't. In fact, I think there were about 20 students in that class, and I asked how many people knew what a p-value is, and I think about 2 out of the 20 did. So the purpose of this video is to clear up any confusion that there may be about p-values, because as we get into the more advanced material in this class, this is something that I want to be a quick and easy go-to. So, guys, trying a new approach here. Usually, I write things out as I'm teaching, but today, or at least in an attempt to save time, I've already gone ahead and written out the notes, and I promise you, I'm not going to read to you. So anyway. A p-value is simply a probability, and you can think about a p-value as indicating how likely that a particular result. Okay, here I go. I'm reading to you, right? How likely? Okay, again, a p-value indicates how likely it is that a result occurred by chance alone. Now, I've kind of given you an example here that I want you to think about, and this is kind of near to my heart now because my daughters are freshmen in high school, and they're starting to think about the ACT. So, and more specifically, they're thinking about raising their ACT. So think about this as a model for what we mean by chance alone. So let's consider an example. Where we have 50 high school students, and they take the ACT the first time, and they get a mean score of 22. Someone has convinced us that we can send our children to a 3-day intense training course geared toward raising ACT scores, and we pay a huge amount, as you would imagine. And then the students take the ACT again, and hopefully there's been an increase in the scores. Well, how do we know, and how can we tap into the training course being the reason for the difference? Because, guys, just by chance alone, these 50 high school students, I don't know about you, but if you have high school children, you know that their mood varies day to day. Well, shoot, their mood varies minute to minute, right? So there's no reason to think they would be able to perform exactly the same, maybe months later. So we expect some sort of what I would call natural variation just by random chance. But when can we tap into that variation as being different enough to where we can give credit to this 3-day intense training course? So again, by chance alone, we'd expect a natural variation. In other words, we would expect the second time that they test that the average for all 50 students would contain some natural variation, that the mean would not be equal to 22. So again, how can we tap into this change being related to this training course and not just by chance alone? Well, guys, the answer to that is something called a p-value. Now, a p-value, we typically need to make a decision. And in order to make a decision, we need a line in the sand, at least as I call it. So, if somebody walks into a classroom and we are defining someone as being tall, well, we need a criteria for what we mean as tall, because to some people, 6 foot is tall. To other people, 6 foot isn't tall. So if we set our line in the sand, and maybe we decide that our line in the sand is 6'4", so anybody at 6'4" or higher is tall. Anyone 6'3" or lower is not tall. Well, we kind of do that in statistics, but our criteria for being quote-unquote tall, the line in the sand, is called alpha. So alpha is a level that is preset. It's usually set at 0.05, 0.10, or zero point 0.01, and it is the criteria by which we get statistical significance. Okay? So again, alpha, this value that we set before we start our test, is the probability of committing a type 1 error. More about that later. In other words, it's the probability of rejecting a true null hypothesis. So guys, most importantly, what I want you guys to tap into here, again, the focus, the emphasis, is that alpha is the decision criteria. If our p-value is less than alpha, we have statistical significance. If our p-value is greater than or equal to alpha, we do not have statistical significance. So guys, looking at these criteria up here, these preset values of alpha, if we get a p-value of 0.038, then we are significant at the 0.05 level because 0.038 is less than 0.05, but we're not significant at the 0.01 level because 0.038 is higher than 0.01. Now, a lot of people play wacky statistics and they get their p-value and they're like, well, I want to get statistical significance, so they just kind of magically set their alpha level at 0.01. It's not the way it works. At least it's not the way it works if you want to play ethically. As I said earlier, the alpha is preset before you begin your test. All right, guys, relationships between samples and population. Population is the entire group of subjects, elements, dogs, cats, trees, whatever it is that we want to investigate. A sample is a subset of the population. In statistics, we hope to work with random samples. And that gets into experimental design, and sometimes you can get random samples, sometimes you can't. Now, the relationship between samples and population vary according to what is known. So if I start with a population where the parameters are known, I can determine the likelihood of getting a particular sample from this population using probability. But I can only do that if I know my population, or I know from which the parameters of the population from which I'm actually collecting my sample. The easiest way to illustrate this is think about a deck of cards. If I have 5 cards, let's just say ace, king, queen, jack, 10, I know my cards. What's the probability of getting an ace? What's 1/5? But what if I don't tell you the cards? What's the probability of getting an ace? Well, you don't know, because maybe there's 4 aces over here and a king. Maybe there's no aces. You must know the population from which you're drawing before you can determine the probability or the likelihood of getting a sample from it. The other direction, your sample is known. Now, guys, back here, let me tell you that the sample is unknown in that direction, and the population is unknown in this direction. So if we're truly at random and we select a sample at random from this population, we don't know what we're going to get, but we can determine the probability of getting a particular characteristic of a sample. Inference is the other way around. The population is unknown. What percentage of people, what percentage of U.S. voters who intend to vote in 2020, or at least in the 2020 election, intend to vote for Donald Trump? I don't know that. I don't know that percentage. But if I wanted to address that, I would go take a random sample, which I would know, because I would take my random sample and I would evaluate the measurements, and I could make an inference or a prediction, if you will, about the unknown value in the population. Well, guys, in moving forward, one of the key things to understand about probability is something called a central limit theorem. And if you look at the textbook definition of a central limit theorem, it says if we begin with a distribution with mean mu and standard deviation sigma given, notice it's known, it's given, the distribution of sample means, the samples that we draw from the population, will be normally distributed with mu x bar equal mu and sigma x bar equals sigma divided by the square root of n if n is greater than or equal to 30. Guys, we actually kind of like 100, but it turns out that 30 works okay. Now, to give you an illustration, I know at all levels this tends to be a little wordy. I was in a graduate class one time and we were talking about this, and surprisingly, quite a few people still didn't have a pretty firm grasp on the central limit theorem. So to give you an illustration to try to strengthen up that understanding of the central limit theorem, let's walk through what we're really doing with this, again, through an illustration. First of all, we start with a mean and a standard deviation that's given, and we have it for some distribution of scores. We select our sample size, bigger than 30. It's real nice if it's bigger than 100. And then we imagine that we start taking random samples. Now, let's just say, for talking this through, that our sample size was 55. So we dive into our distribution, pull out 55 random measurements, take the 55 measurements, add them up, divide by 55, we get our first sample mean of size 55. Again, select the sample and keep it consistent through all the samples. Throw those 55 back in the mix, close your eyes, randomly select another 55 measurements, add them up, divide by 55, you get your second sample mean for 55 measurements from this population, randomly drawn. Imagine doing that again and again and again and again and again. Imagine doing that forever. Now, you don't have to do it forever, but it's just theoretically, think that you could just forever create random samples of size 55 from your population. Well, guys, at the end of the day, you just end up with a lot of random samples, don't you? And we call these things the distribution of sample means x bar. So these scores from these means become a new distribution, not the distribution we started with. This is a new distribution. The distribution we started with was the distribution of measurements from that distribution. These are the distribution of sample means from that distribution, taken 55 at a time, as used as an example. Central limit theorem tells us three things. First thing it tells us is the distribution of sample means will be normally distributed. It tells us that the center of the distribution will be the mean that we started with, and it tells us the standard deviation of the distribution will be the population standard deviation divided by the square root of n. Now, I just gave you an example here, something that we can do in R. So let me pull up R. So the problem here is we know that ACTs are normally distributed, and it probably would help if we could read this together. So yeah. So ACTs normally distributed, mean of 21, standard deviation 5.5. We collect a random sample of 42 ACT test takers. What's the probability that their mean ACT is higher than 22? So we'll use R for this. So guys, R, I can use P norm. The first thing I want is the value. So in this case, it would be the mean of 22. The next thing I need is the mean of the distribution, which is 21. And the next thing I need is the standard deviation, which is 5.5 divided by the square root of 42. Now, guys, this is going to give us below. So P norm is set to give you below. So I need to take 1 minus this to get above. The area under the curve, normal distribution, is equal to 1. So if I get the area below to find the opposite area, the area above, all I need to do is subtract that from 1. So guys, when I get my answer, the probability would be 0.119. Easy stuff, right? R is very powerful and sometimes really, really easy to use. Now, guys, what I want to do now is I want to change directions instead of, and I just gave you a very, very straightforward example of probability. I want to change directions now and start thinking about inference. So I want to set the foundation for the inference component of applied linear regression in this class. Now, guys, first week I'm trying to keep it pretty simple. I'm trying to brush up on your undergraduate statistics because, again, as I told you earlier, I've taught this class. I think I've taught it 5 times now. The most epic fails that I've had is where I assumed that students knew too much. So I don't want to leave anything without at least covering it briefly. So, guys, in inference, there's 2 things that we kind of think about. One is estimation. That's a confidence interval, and 2 is hypothesis testing, where there is a claim about a parameter or value, and we use sample data to actually to test that. Now, slight caveat: the central limit theorem depended on knowing sigma. It depended on knowing the population standard deviation. But guys, typically the population standard deviation is not known. So insert when this isn't the case, instead of the z distribution, mean 0, standard deviation 1, we depend on the t distribution, which is defined by the degrees of freedom. And guys, degrees of freedom for the one sample mean problems is very easy to find. It's just your sample size minus 1. It's going to become clear, I think, once we get into an illustration. So, guys, again, back to p-values, which we're really this is all about. Remember, to calculate a p-value, we must know the underlying probability distribution. So, guys, if we have a claim about a population mean and the population standard deviation is known, it's very, very rare, we can work with the z distribution. If we have a claim about a population mean and the population standard deviation is not known, which is typically the case, we use the t distribution. If we have a claim about a percentage, z distribution, guys, we're going to get into ANOVA and test of independence and test of goodness of fit, and that's the place where we use the chi-square distribution. So depending on the type of problem that we're investigating, the distribution that serves as the underlying probability distribution can change. The illustration that I want to give in this video, which certainly can be generalized, is using the t distribution. All right, so let's just work through a simple problem. Estimation, we'd like to estimate the mean wait time at Tim Hortons from 8 a.m. to 9 a.m. in the morning. Now, obviously, I think it would be different from 8 a.m. to 9 a.m. than it would be maybe 3 o'clock to 4 o'clock. I don't know that to be true. I don't know anything about the wait time at Tim Hortons. So, guys, we go in and we take a sample. So 5 measurements. The first time we went, it was 3.5 minutes. Next time, 4, and so on and so forth. So the first thing I would do is create my point estimate, find the sample mean. Sum is 221 divided by 5. So on average, I waited 4.42 minutes to receive my food after ordering it. Well, no, actually, that was after getting in line. So 4.42 minutes. To create a confidence interval using this point estimate, we would take the point estimate as the center and we would add or subtract margin of error. Now, why? Well, the reason we want to add margin of error is because there's nothing holy about this 4.42. If I had gone back another week or maybe at a different time during this time segment, these weights would have varied. So this 4.42, although it's important to me because it's the 5 measurements that I took, and by the way, these are made-up numbers, so don't go rushing to Tim Horton and you do this and you have to wait 10 minutes and you claim some sort of bias because Dr. Darber only waited 4.4. No. These are made up, so don't be too hard on on Tim Horton, okay? If you have to wait longer. or don't give Tim Horton too much credit if you are quicker. So anyway, we would have margin of error because this point estimate will vary from sample to sample. We saw that back in the central limit theorem, where if we took out samples 55 at a time, we expect some sort of variation, and we can explain that variation by the standard error. Standard deviation, or I'm sorry, the confidence interval formula is the sample mean. This stuff over here is your margin of error. This is your T critical, and this is your standard error. So we'd like to estimate within 95% confidence. So guys, first thing we need to do is calculate T star. And again, we need to do it for the T distribution degrees of freedom 4. So let me explain to you how I come up with this 2.776. It's very easy again. Just go to R. And instead of using P norm this time, I'm going to use the T distribution. But I'm going to change two things. First of all, I don't use the P norm because if I think about the P function, it takes a particular value from the normal distribution and finds the area below it. Or when I subtract it from 1, it finds the area above. What I want to use is I want to use a Q function which takes an area below and tells me the value from the distribution that meets that criteria. I also want to use the T function, or I'm sorry, the T distribution instead of the normal distribution. So I use T instead of norm. So I'd use a different, instead of P, I use Q because I want to find a value from a distribution. It has a certain percentage of the distribution below it. And I use T because it's a T distribution. Well, guys, going back over to the drawing, if I look at, I've got 0.9, or I've got 95% between these two values because I'm trying to find a 95% confidence interval. Let me see if I can make that just a little bit clearer. Okay, and so I'm missing 5%. Well, I want to put half of the 5% here, and I have half of the 5% there because I have, again, perfect symmetric distribution. So I need to find the value from the T distribution, degrees of freedom 4, that has 2.5% of the area under the curve below it. So guys, I do that by putting in 0.025 degrees of freedom 4, and I can see that I get negative 2.776445, which is what I have on the sheet of paper. To find the other, I can just use the positive of it because I have symmetry, or if that doesn't do it for you, I can put 0.975 because that would be the area below the upper part of the 95%. So I get 2.776445, same thing except the positive. So guys, hopefully that makes sense why negative 2.776 and positive 2.776 are our T criticals for this problem. Next thing, plug and chug. Insert the mean, insert the T critical, standard deviation divided by the square root of n to make the standard error. And guys, we get the 95% confidence interval to be 2.53 to 6.31. So what we can say here, I'm not going to write it out, but what we can say is there's a 0.95 probability that the mean wait time for all people, not just me, but for all people from 8 a.m. to 9 a.m. Is contained in this interval. Actually, technically, there's a 0.95 probability that this interval contains that unknown amount or unknown measurement. Margin of error is easy to find. Take the big number minus the small number divided by 2. And you get plus or minus 1.89. Now, back to p-values. Pretty much everything I've done so far is just kind of set up the foundation for these p-values. So let's go back to this Tim Hortons problem, and let's test a claim. Let's say someone said, well, I think it takes about 8 minutes for the average person, or a person on average, to wait to be served Tim Hortons. So guys, we're going to set it up in terms of our null hypothesis. We're going to test the claim that the mean wait time is 8 minutes versus the mean wait time is not 8 minutes. We set our line in the sand as we typically do, 0.05. Step one is determine the underlying probability distribution, but guys, we know that's a t-distribution, degrees of freedom n minus 1. So the first thing we would do is calculate the test statistic. We take the point estimate minus the claim divided by the standard error. So our point estimate was 4.42, our claim in the null hypothesis was 8, and our standard error is 1.525 divided by the square root of 5. Guys, our test statistic is negative 5.25. We insert this value on our t-distribution, so the p-value is the area outside that range of negative 5.25, but we also have to account for the 5.25 because we're doing a two-tailed test, not equal to. So this area is as equally likely as this area. So I'm going to focus on this area right here, and I'm going to show you how I come up with the 0.0031. I multiply it by 2 to account for this area up here. So my p-value is 0.0062. So negative 5.25. Guys, let me show you how you do that. So we're going to go back now to the t-norm. The pt. So I want 1 minus pt, and I want negative 5.25, and I have degrees of freedom equal to 4. Now this is going to give me the area, sorry, I don't need the 1 minus there, because pt gives me the area below. So I can take this and I can just go ahead and multiply by 2 because I have to account for both. And I get 0.006, actually 0.0063, rounded correctly. So back to what can we conclude? Well, we have statistical significance because our p-value is less than our line in the sand, 0.05, so we have statistical significance again. So we can say that the difference in the point estimate and the claim, mu equal 8, is due to more than just chance alone. Because guys, think about it. Day in, day out, minute in, minute out, you're going to expect your wait time to vary because conditions change. Maybe people are having a bad day. Maybe more customers, whatever it may be. Maybe the coffee machine breaks down. Maybe the coffee, there's all sorts of things that create a natural variation in wait times at a local restaurant. So guys, let's just kind of put the dot the I and cross the T here. What's a p-value? A p-value is if the null hypothesis is true, it's the probability of getting the point estimate that we got from our sample, that we get that value or something more extreme. So it's kind of in relation to the null hypothesis being true because we're making this collection, the sample mean, these measurements, under the truth of the null hypothesis. In this situation, we have statistical significance which says we have evidence against the null hypothesis. So based on our sample data, it is more reasonable to conclude that the alternative hypothesis is true than the truth of the null hypothesis. All right, guys, that's all I got. Take care.